Hi team, this is Sean with Alexander Tutoring. Today I want to do our patented 8-step method for solving physics problems. So I came up with this method with a lot of influence from my professors in college, and here's why. So a problem we see all the time is we get these like straight A math students who had got a C in physics and they're freaking out. And here's why that happens. So good math students have learned that they can follow a set of steps like a recipe to get from point A to point B. So when they approach a math problem, they just figured out they can learn a series of steps, memorize the steps, and if they perform them accurately, they'll get from point A to point B and get the A in the class. Now, what happens when they hit their first physics class is there's no recipe, there's no steps. And so what happens is these students sit down to try and figure out a physics problem, and they end up like they're good students, they're putting the time in, but they end up spending hours of just trying to quote unquote figure out the problem. And the problem is they get lost in outer space. They just go in circles, and they basically walk away from their 2 hours of work without any product for the time they put in. And so our goal is to really make your time work for you. I always tell all our parents that tutoring doesn't get you out of any work, but what it does do is make the work that you put in ultra efficient. Okay, so to solve this problem, we came up with an 8-step method for approaching physics problems. And what this does is it taps into the part of your student that succeeded in math, that part of them that was able to learn a recipe or a set of steps. And then what it does is it really turns a whole bunch of different problems into the same problem. Because what happens in physics is it seems like all the problems are totally different. Like one's going to be a cannon shooting something off a cliff. Another one's going to be a bird dropping a rock while it's flying. Another one's going to be a kayak paddling up a river. Seems like they're all totally different problems. They're totally the same. So I want to show you how we can apply my 8-step method to a physics problem, and it'll get you to the answer every time. Okay, so I wrote out the 8 steps here. You can see them up top. And then right here, I've made a physics problem for you. This is like a totally classic type of kinematics problem that you would see in basically every physics class. So the trick is not to focus on the problem, focus on the steps. Okay, so let's read it. A cannon is used by the Department of Forestry to launch containers of fire retardant onto a fire. The cannon is on the edge of a 100-meter high cliff and can fire the retardant with an initial speed of 30 meters per second at an angle of 30 degrees above the horizontal. Okay, so that would be how far can the cannon shoot the retardant? What's the range, basically? Okay, so that would be a totally typical high school kinematics problem. Okay, so start with step 1. Draw a large picture. Okay, those words are very intentionally chosen. Why do I use the word large? Because almost all students, for whatever reason, like to make microscopic pictures. And the problem with that is once we get farther down the steps, basically, you're going to run into issues with your drawing. So you really want to just make it a big drawing, you know. I think we're all taught to save paper, which is great, but drawing your picture is not the time. Okay, so here's obviously a fire down here, and then we have our cannon at the top of the cliff, firing at a 30-degree angle. Okay, you don't have to be a great artist. And what's the question asking for? It's asking for the distance, or the farthest distance it can shoot. Okay, so that's step 1. There's our large picture. Step 2, the most overlooked of them all, put in a coordinate system or an XY axis. Students will do absolutely anything in their power to not put it in an XY axis, and it leads to the most common mistake in high school physics, which is sign errors based on your coordinate system. So the importance of coordinates, so I'm going to make an XY axis, is that it defines all your quantities. And it defines what direction is negative and which direction is positive. Okay, so we've defined to the right, this way, to be positive x, and we've defined up to be positive y. Now, we didn't have to do that. We could have flipped those things around. It's totally fine. What is important is that you define your coordinate system and that you stick to it. Okay, and this is what we're calling 0 right down at the bottom of the cliff. Step 3, draw a vector to represent the initial velocity of the object. Okay, so we're firing this thing from the cannon, right? So it's going to leave the cannon. With an initial velocity of, what did I say? 30 meters a second. In other words, the length of that velocity vector is 30 meters per second. If you don't understand how length can be a velocity, we'll save that for another lesson. Okay, so there's a vector to represent the initial velocity of the object. If the vector, step 4, if the vector is not perpendicular to the coordinate axes, break it into x and y components. Okay, so you can see that our initial velocity vector is neither parallel to the x or y axis. So we're going to break it into components. So we're going to draw in its x components. Now you can see why I demanded a large picture, right? Because if you made a microscopic picture at this step, it would just get unreadable. Okay, so there's the x and y components. This angle is also 30 degrees. And so we need to figure out the magnitudes or the lengths of those components. And we're going to use our classic sines and cosines, which I'll assume you know. Okay, so we know that sine of theta is equal to the opposite over the hypotenuse. Okay, so in this case, we have the sine of 30 degrees is equal to the opposite side of the triangle, which is the y component. In this case, that would be this guy. Excuse me. Okay, so I'll call that V0y. Positive, because it's pointing up, divided by the hypotenuse, which we know to be 30 meters per second. Okay, multiplying both sides by 30 meters per second. We find that the y component of the initial velocity is 30 sine 30. Now the sine of 30 degrees happens to be 1/2. Again, if you're not sure why, you can always use your calculator. But I've just memorized that special angle. 15. Okay, so the y component of the initial velocity is 15 meters per second. What's the physical interpretation of that? It means that the instant that the cannon is, the fire retardant is fired, at that instant, it's gaining altitude at a rate of 15 meters a second. Okay, and then we need our x component, for which we'll use cosine. Actually, let me just do this little thing. So we'll say, I'll start from cosine. We'll say cosine 30 equals adjacent this time, which is the x component of the initial velocity over the hypotenuse. Again, 30 meters per second. Go a little quicker this time. Multiply both sides by 30. And the x component of the initial velocity is 30 times the cosine of 30. And the cosine of 30, I just happen to know, is root 3 over 2. It's a special value. You can always use your calculator. Call that 30 over 1. And we get 15 root 3 meters per second. What is the physical interpretation of this? That's the x component. That's this guy. So we have 15 meters per second. And 15. Okay, so what that means is that after the fire retardant is fired, it's moving in the x direction or making progress down the x-axis at a rate of 15 root 3 meters per second. Okay, and that in fact is going to be constant for the entire flight because we're assuming no air resistance. And if there's no air resistance, there's no forces pushing left or right in this problem. And so that means that according to Newton's second law, that the x component of velocity will remain constant the entire flight. Now there is a force acting in the y direction. That, of course, is the force of gravity, which goes along with an acceleration due to gravity of 9.8 meters per second squared. Okay. All right. So let's. We finished step 4. We broke them into x and y components. Step 5. Make a table of known and unknown values, one for the x direction, one for the y direction. Okay. And here's the values that I'm referring to. We want to know the initial position of our projectile. We want to know our final position of our projectile. We want to know the initial velocity. We want to know the final velocity. We want to know the acceleration. We want to know the time. And we want to know each of these quantities for both the x direction and the y direction. So I'm going to make 2 columns for each because this is a 2-dimensional problem. Okay? So let's start with the x values. What is the initial position? And that is to say, because we're only looking at the x component of things, what is the initial x coordinate of the projectile? Okay, well, this is where the coordinate system becomes really important. We started with our origin here, so the cannonball starts here. That x coordinate is 0, so it's starting from x equals 0. What's the final position of our cannonball? Well, it's going to do this, right? And so the final position is basically what the problem is asking for, right? That's how far it can shoot the cannonball. So that's what we are interested in. That's what the whole problem is asking for. So I'll put a question mark there. What's the x component? Again, remember, we're only looking at x values here. So what's the x component of the initial velocity? We already figured that out, 15 root 3. What's the final x component of the initial velocity? Well, we just argued there's no forces in the x direction, so it's going to remain a constant the entire trip according to Newton's second law. So the final will be the same as the initial, and what that means by the definition of acceleration is the acceleration is 0. Acceleration is a change in velocity, and it didn't change, so that makes it a 0. And then time, we don't know how long the time the trip takes. So we'll put a question mark there. So you can see there's 2 question marks, there's 2 quantities we don't know, and there's a few 4 that we do. Okay, now we're going to do the exact same thing for the y direction. Okay, so what's the initial y coordinate of the projectile? Well, we know it starts on top of a 100-meter cliff, right? So the initial y coordinate, the starting y coordinate of the projectile is all the way up at 100 meters. Again, this is why our coordinate system is so important. We could have made the coordinate system on the top of the cliff, but it would have changed our values. Okay, so initial y coordinate is 100 meters. Final y coordinate is down here, right? What's the y coordinate of that point? It's on the ground, so that's 0. That's a known. What is the y component of the initial velocity? Well, good thing we did that earlier. That's this guy, 15 meters a second. What's the final y component of the velocity vector? Well, that would be basically what that's asking is they're talking about the velocity vector of the projectile right the instant before it hits the ground. Okay, so the components are going to look something like this at that instant, right before it hits the ground. So what it's asking for is this guy. We don't know what that is yet, so I'm going to put a question mark there. Okay, what's the acceleration in the y direction? Well, there's an acceleration in the y direction caused by the acceleration due to Earth's gravity. Now, here's another big place where sine errors tend to come in. The acceleration due to Earth's gravity is 9.8 meters per second squared. And in this case, because this vector is pointing, it always points towards the center of the Earth. And because we defined up to be this way, we have to make it negative. Now, a really common mistake, one of the most common ones, is that students think that the acceleration due to gravity is just negative. It's negative 9.8 no matter what. And that's not true. It's your choice of coordinates that makes it negative. I could have just as easily made my coordinate system, that's a y, like that. And then the acceleration due to gravity would be positive because I defined down to be positive. Okay, so there's nothing inherently negative about the acceleration due to gravity. It is always and forever pointing towards the center of the Earth, but that's not what makes it negative. It's your choice of coordinate system that, in this case, makes it negative because I defined up to be positive. So that's a big point of confusion. But for our case, this will be negative 9.8 meters per second squared. And the time to complete the trip, we don't know. And this time is the same as that time because time is not a vector, so it doesn't have an x or y component. Okay, we finished another step. So again, the trick is not to think about the particulars like it's a forest department or whatever. It's irrelevant. The point is to stick to my steps no matter what, and it will get you to the right answer. Okay, so step 6, starting with the y values, pick the one of the 3 kinematics equations that has all known quantities plus a quantity you need to find. Okay, so basically we want to look at our y direction first. Almost always that's the case. And we want to pick one of the 3 kinematics equations. Let's write those down so we can see them. Okay, these are like our choices of kinematics equations to choose from. So looking at the y direction, we want to, what don't we know? We don't know v final, we don't know time. Time would be great to know. And so we want to pick one of the three equations that basically has a t in it because we want to find time. And then where we basically know all the other quantities are known. So looking at the first equation, v final, we don't know that, so I don't want to use that one, right? Right, we agreed we don't know the final y component. What about this one? X final. Well, we know that. We know x final. We know, actually, I should really say y final because we're looking at the y direction. We know the final y coordinate. We know the initial y component of the initial velocity. We know a, and we want to find t. So that fits the bill, right? We want to find t, and we know everything else. So we're going to pick equation number 2 and fill it in. And the good news is at this point, you've already put all your information in. It's easy. Okay, so it's just filling stuff out. So the final y coordinate we agreed is here, right? 0 equals the initial y coordinate, 100, plus the y component of the initial velocity, which we agreed was 15 meters per second, times t, which we are trying to find, plus 1/2 a. Just to make my life easy, I'm going to make this 10, guys. Some classes do that. Just makes the math easier. So I'm going to round it to negative 10 meters per second squared times t squared. Okay, so now we can theoretically solve for t. I'm going to simplify first. We get 0. I'm going to leave the units out for now. And you can see here, what do we have? We have ourselves a quadratic equation, which can be solved for t. Okay, so for those of you who don't know the quadratic equation, I'm tempted to sing the song. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Can't believe I did that. I swear I would never do it. Okay, so in this case, a is negative 5, b is 15, c is 100. So we have x equals negative 15 plus or minus the square root of 15 squared minus 4 times negative 5, signs matter, c all over 2a, which is negative 5. Okay, so I need some calculator action here. 15 squared is 225. And that's 20 times 100. Minus is a plus. 2,000 over negative 10. You can see that physics is an involved class, not easy by any means. That's 2225 over negative 10. The square root of 2,000 is not pretty. Let me see if I can write that a little nicer. Well, no. Roughly 47.2. Okay, now there's two solutions. One's going to be negative and one's going to be positive. However, keep in mind we're solving for time here. Maybe I should have used a t here because in that case. And as far as we know, at least for the level of this class, time cannot be negative. So we're going to throw away the negative solution and just keep the positive one. Okay, so the one that's going to give us the negative, or excuse me, the positive solution is when we take the minus sign. So we do negative 15 minus 47.2 is negative 62.2 divided by negative 10. That makes it positive. Is roughly 6.22 seconds. Okay. Okie dokie. Next. So we just solved for t. Let's go back up to our chart. We know what t is now. And again, it's the same in both columns, so it's roughly 6.22 seconds. That's how long the projectile is in the air for. Okay, let's see what step we're on. 7. Take the newfound quantity over to the x side of the table, which we did, and repeat step 6 for the x value. Step 6 is we're going to apply a kinematics equation to solve for the thing we're trying to figure out. You now have a system of equations that can be solved for whatever quantity the problem asks for. Okay, so the cool thing about this process is like you don't even have to all the like the forestry, the fire retardants, totally irrelevant. What it allows you to do is just suck the relevant information right out and get you right to the answer. Okay, so now we're looking at the x column here, and we want to find the kinematics about that. And the okay, so looking at the x column, we want to find x final. This guy is what the equation is. That's what the whole problem is asking for. Okay, so let's look at the first equation, v final. Remember, this is the x component now. We know. V initial we know. And a is 0. Sorry, but that doesn't have x final. That's what we're trying to find. X final. This is what we want. Okay, so equation 2 has x final, which is what we want. We know x initial, we know v naught initial, and we know the acceleration. So that is going to be our guy. So this will be much easier. I'll just do it over here. So x final is what we're trying to find. Equals x initial, 0, plus v initial, t, leaving out the units for now, plus 1/2 at squared, but a is 0. So really, look how much easier that was. X final is 15. T, and 2 we know, is 6.22. Okay, so let me just do that on my calculator. Root 3 times 6.22 times 15. X final, which is what the problem is asked for, equals 161.6 meters. Boom. That was a lot of work, huh? Physics is hard. Okay, however, my set of steps, really what I want your student to focus on is just, don't worry about the problem, just do the steps, one after the other. Now, the last step, step 8, is very important. Most students like to skip this one. Check to make sure your answer makes sense. Why is this important? Because if you make any mistake in high school physics, like if I made even the slightest little sign error or tiny mistake in this whole long involved process, almost always the answer that you get is totally ridiculous compared to the numbers involved in the problem. Like, so, you know, if I was solving for x final, the thing that this thing can shoot, and I get an answer like 0.00359 meters, you would look at the problem and be like, that's probably ridiculous because it's 100 meters off a cliff, shooting at 30 meters a second, which is fast. There's no way it's going to go like a fraction of a meter, right? Okay, so let's ask, does our numbers make sense? We got a hang time that's going to be in the air for 6.22 seconds, which for, project, that's a long time. 1,000, 2,000, 3,000. For a projectile, it's long, but it's up on a big cliff, so that seems reasonable to me. Finally, our range, that went a distance of 161 meters. That sounds reasonable to me, given the scale. You can see it's a 100-meter cliff, so you can see this is all numbers in the ballpark of the problem. And so I am satisfied with those numbers, and that is an example of how our 8-step method can be used to solve a whole ton of different physics problems that are going to seem totally different. They're really all the same problem, and if you follow our steps, it'll get you to the right answer every time. Okay, that was a long one. Thanks for watching, guys. Take care.